Yeah, I'd like to thank Thomas and the other organizers for putting this together. It's a treat to be here and get to talk to this community of people interested in finiteness and tameness questions, which I think is a really important and interesting set of questions on the physics side, and it seems also on the math side has a lot of interesting aspects. So I'm going to try to give a talk today in the spirit of this conference. I'm used to giving physics slide talks with lots of slides and graphs and things and lots more information than you can absorb. But I'll try to just cover the key points in this talk. Let's see, do we have white Hagoromo in anything? Yeah, let's do this one. Good. So let me start with a little bit of an overview. So this is about Calabi-Yau manifolds, Calabi-Yau threefolds in particular. And I know people are coming from different directions, so I'll give a little bit of an introduction to some of the basic ideas. So we're talking about Calabi-Yau manifolds and threefolds in particular. So mathematically, a Calabi-Yau variety or a Calabi-Yau threefold is defined as having a vanishing anti-canonical class or first Chern class, which is mathematically equivalent by Yau's theorem and various other results to the statement, first of all, that this is a Kähler manifold with, if for a threefold, SU3 holonomy, which is important to physicists because it means that if we use a Calabi-Yau manifold to compactify space-time, so the picture for the string theorist underlying all this is that we have some 10-dimensional manifold, which is compactified down to our space-time dimension, perhaps, which is R3, 1, on some Calabi-Yau manifold. So this is a CY3 times R3, 1. And the idea is we take 10 dimensions, we make 6 of them small, we curl them up on some tiny space, which in our case is going to be a Calabi-Yau. And if that tiny space has SU3 holonomy, it means that we preserve some supersymmetry, which is great for string theorists because we still have a lot of mathematical control. And we have the power of holomorphy and analyticity. At the same time, this also means that the space has a Ricci flat that it admits a Ricci flat Kähler metric, which means we can solve Einstein's equations. And that's the thing that allows us to have a solution of the 10-dimensional gravity equations on the Calabi-Yau, which gives us flat 4-dimensional space-time. So this is why we want these things from physics. And mathematically, the Calabi-Yau is just characterized by the vanishing of these topological features. So physicists and mathematicians have been excitedly studying Calabi-Yau manifolds for about 4 decades now, and we know lots about them. We have many examples. Much of what I'll talk about today is some of those many examples and some things that we've learned about them recently. But there are some fundamental questions. Are there a finite number of topological types of Calabi-Yau threefolds? Despite decades of work, we do not have a clear answer to that question. The second question is, are they all connected? In other words, is there a big moduli space where you can go from one Calabi-Yau to another by some kind of extremal transition? There are extremal transitions between many pairs of Calabi-Yaus. The general question is, are all Calabi-Yau threefolds, the smooth ones, connected by extremal transitions through singular intermediates into one connected moduli space? This is called Reid's fantasy. And I'm going to talk a little bit today about each of these questions. I think in the context of this workshop, there's a natural other question, which is the moduli space of Calabi-Yau threefolds, assume it's perhaps finite and connected, is that moduli space tame? And maybe you all would say as soon as it's finite, it's tame, but I'm not sure if that's right. There are a lot of complicated functions. I'm curious to get takes from some of you on this question. And this is kind of related to these two, but a little distinct. So the outline of what I'm going to do, I always have a lot more to say than I have time, but I'll try to cover all 3 of these points. Is first of all, I'm going to talk about, yes, please.
when you said that modulus, you mean moduli up to what? Because the finiteness was for topological types. You mean the modular space?
So, okay, for each topological type, there's a moduli space parameterized by complex structure moduli and Kähler moduli. So we can visualize the moduli space. Here's the moduli space of the quintic Calabi-Yau, which is a quintic hypersurface in P4. It's got 101 complex structure moduli. It's some moduli space. It's connected through extremal transitions to some other Calabi-Yau, where you do some conifold or some other transition. So the finiteness is the number of regions or the number of smooth patches connected to each other by some kind of singular transition. That's what I mean by, so everything in this continuous piece of the moduli space is a single topological type.
Yeah,
Does
I
this?
just want to make sure. I mean, so it's not really a finite space, it's a finite number of components.
It's a finite number of components, exactly, yeah. It's a continuous moduli space, and it's very high dimensional. So the question is there some sense in which this is, I mean, it's a very concrete question, are there a finite number of topological types? Very concrete question, is it connected? And one could imagine, is it tame? Is there some way of defining this moduli space as a variety in some huge dimensional projective space, which it could be controlled by a finite number of polynomials in a well-defined way? That would be even a step beyond Reid's fantasy and the finiteness. Great, okay. I encourage questions. If I don't get through quite as much material, but we have discussion, that's great. So just pipe up if something is unclear or you want to talk about something. So first I'm going to talk about two of the biggest classes of Calabi-Yaus that we know about. One of them are the toric hypersurface Calabi-Yaus, and the other one are elliptic Calabi-Yaus. And each of these has some very interesting and nice properties. And the theme of the talk is essentially bringing together those two big sets, looking at the overlap, how to think about those. The second part of the talk will be about fibrations, the elliptic fibrations of these many Calabi-Yaus as a lens on the Calabi-Yau moduli space. And in particular, I'll talk about a paper that conveniently came out last night with Fatima Abbasi, who is just recently graduated undergrad from MIT, Richard Nally, who's here in the audience. And the number, if I remember correctly, is 2511.10601. Is that right, Richard?
Yep.
Great. It came out just a few hours ago, so you're fresh off the presses. And then the third thing I'll talk about, given time, is how to then think about, through this lens of fibrations, finiteness and connectivity. And I'm going to talk about some fun results that we're in the process of developing with Anderson, Gray, and Nally. Work in progress, where I think we have some interesting things to say about this. So I'm a physicist. I'm going to use primarily data, not theorems. I will quote some theorems by other great people, and I will provide you with some of what I think is very interesting data, which suggests natural answers to some of these questions. But I'm not going to prove big theorems. Okay, so that's the setup. Any questions about the setup? Okay, so let's talk briefly about each of these two kinds of Calabi-Yaus, the toric hypersurface Calabi-Yaus and the elliptic Calabi-Yaus. Okay, so 1A, let's just remind everybody what a toric variety is. So a toric variety is kind of a poor man's algebraic geometry. I like toric geometry because I can just use simple combinatorial approaches to doing fairly complicated things with concrete algebraic varieties without having to worry about schemes and motives and all those things. I can't draw a picture of a motive either. I couldn't even imagine drawing a picture of a motive. So I can, however, draw a picture of a toric variety. So our simplest toric variety is, P2, complex two-dimensional projective space. Just to remind you how this works, we can think of this as kind of an inversion of a picture of P2, where the point at the origin is C star squared, and then each of these things is a divisor. So the dimensionality is, as you know, kind of flipped. So this is the biggest dimensional thing is the point, then we have divisors, and then these things are points. And so really to define a toric variety, we have a set of rays, VI, and a fan, sigma, and the fan is basically a set of cones with various properties that fill the, if it's compact, they fill the space. So compact if and only if the fan is complete. And this essentially defines a toric variety. From the VIs, we can construct a polytope. I'll call them nabla. So the polytope is the convex hull of the set of points spanned by the rays. So that's the general idea of a toric variety. Hopefully some of you have you're mostly mathematicians who I assume have seen a little bit of toric variety sometime, but basically the idea is it's just a nice simple combinatorial way of encoding lots and lots of interesting algebraic varieties. Not the really fancy stuff, but enough to get us going pretty far, as we'll see. One key feature is that the anti-canonical class of a toric variety is given by the sum of, so each VI is associated with a divisor DI, and the anti-canonical class is given by the sum of the divisors. So for instance, for P2, there's certain linear equivalence relations given by the Stanley-Reisner ideal. So there's two equivalence relations for a 2D polytope. This is the same divisor as this, and this is the same divisor as this. So in the anti-canonical class of P2, this is just 3H. It's 3 rays, each of which is equivalent. So we can just read off the anti-canonical class from the toric variety. Great. Okay, let's talk for a second about polytopes. As I say, from a toric variety, we can get a polytope. Just erase that so I can continue here. If we have a polytope nabla, we can construct a dual polytope nabla circle, which is the set of W in Zn such that, sorry, actually, let's do it this way. W such that W comma VI is greater than or equal to -1 for all I. So it's the dual polytope given by inner products bigger than or equal to -1. So for instance, for P2, the dual polytope looks something like this. It's this set of lattice points. We have some nice colors, so we'll do it in color. Yeah, so the dual polytope looks like this. And polytope is reflexive if and only if its dual polytope is a lattice polytope. And it has the interior point property, meaning that it contains the origin as an interior point, not on the boundary. So the P2 clearly has the interior point property. Its dual polytope is a lattice polytope, so it's a nice reflexive polytope. Okay, so this allows us to construct a variety, a set, I mean, I use the word variety, a large set of toric varieties in various dimensions. And using the adjunction formula, there's a beautiful result of Badarev, which showed that if you take the anti-canonical hypersurface in a toric variety defined by a polytope nabla, where nabla is reflexive, then we get a Calabi-Yau. And it's generally smooth. It avoids singular points in the ambient polytope. And there's a combinatorial way of computing all the stuff you want to know about the Calabi-Yau, like the Hodge numbers, directly from the data of the toric variety. So again, given a nabla, given a polytope, we would need to construct a fan, and there are various different ways of doing that. But this is a nice way of constructing Calabi-Yaus. So let me tell you two facts. One is, in 2 dimensions, there are 16 reflexive 2D polytopes. That includes P2 and a few others that we'll talk about. And Karitzer and Skarka categorized the 4D reflexive polytopes a number of years back, and there are 473,800,000 1,776 four-dimensional reflexive polytopes. So this is actually the biggest database of known Calabi-Yau threefolds. You take one of the 474 million Kreutzer-Skarka reflexive 4D polytopes, you construct an anti-canonical hypersurface, and you get a Calabi-Yau. Huge database. You can look it up online and download data sets. This is where the business of data comes in that I mentioned. Okay, so that's one piece of what we're going to talk about is these Kreutzer-Skarka toric hypersurface Calabi-Yaus. Any questions about that? Okay, now let's talk about elliptic Calabi-Yau threefolds. And by the way, this set is obviously finite, but it's obviously a substantial subset of all Calabi-Yaus, or it's not obviously, but it is a substantial subset of all Calabi-Yaus, and we can talk about how far it goes. But now let's talk about elliptic, or genus 1, fibered Calabi-Yaus. Okay, so let's remind ourselves about an elliptic curve. So one way of thinking about an elliptic curve is we can look at the, use my colors. We can look at the toric variety, 1, 2, 3, sorry, I've drawn that wrong. Let's look at P231, where this. So here's another 2D reflexive polytope. It's P231. And this is another 2D reflexive polytope. The dual to that polytope is this polytope. And so by writing a polynomial in its quasi-homogeneous coordinates of P231, where the different elements of the polynomial are given, the different monomials in the polynomial are given by these lattice points, we can write down a general form for an elliptic curve, y squared plus a1 y x. I'll look in a patch where z equals 1 for convenience, plus a3y equals x cubed plus a2x squared plus a4x. This is the standard long form, Weierstrass form for an elliptic curve. So this is an elliptic curve, and it's easy to see that the double cover of P1, which is branched at 4 points, so it's definitely a torus, and it's got a marked point, which is 1, 1, 0, which is the point that we need to make a torus into an elliptic curve. Okay? And given an elliptic curve, we can always write it in short Weierstrass form by completing the square and the cube. So then we get y cubed squared equals x cubed plus fx plus g. And this parameterizes a torus with a point. Okay, all good so far, right? Okay, now let's do something slightly more fancy, which is take this elliptic curve and fiber it over some base. So given a compact scalar B2 with a positive anticanonical class, if we write y squared equals x cubed plus fx plus g, where f is a section of O of minus 4k and g is a section of O of minus 6k, then this is actually an elliptically fibered Calabi-Yau threefold on the base B2, right? So now we have an elliptic curve, we have x, we have D2, and this Weierstrass model gives us an elliptically fibered Calabi-Yau. So this is a large class of Calabi-Yau manifolds where we choose a compact scalar B2 with certain properties, which I'll mention in a minute, such that the anticanonical class is positive, and we choose a Weierstrass model where we take f and g as sections of certain bundles over this base, okay? So this gives us, geometrically sort of a picture of an elliptic Calabi-Yau, and this is a huge class of Calabi-Yaus. If we take a base like B2 is P2, We can look at the generic elliptic fibration, and it gives us Calabi-Yau with Hodge numbers 2, 272, typical Calabi-Yau. But we can do many more things. We can look at more complicated bases, or we can tune the Weierstrass model until some of the fibers become singular, and we get some kind of singularity that we have to resolve, and we get a more complicated Calabi-Yau. So codimension 1 singularities in the fibration were classified in a beautiful work years ago by Kodaira. And so it turns out by just looking at the order of vanishing of F and G and delta, the discriminant, so the singular fibers occur at delta is 4F cubed plus 27G squared. Those are the singular fibers. And the type of singularity was classified by Kodaira, and I'll just give you a little piece of the table. Basically, the order of vanishing of F and G and delta allow you to read off the singularity type. So for instance, a singularity in delta, which is not, where there's no vanishing of F and G to order n, gives us what's called an IN singularity. And if we resolve it, we get an affine Dynkin diagram of the type AN minus 1. And things get more complicated as the order of vanishing of F and G goes up, and eventually we get up to 4, 5, 10, at which point we have a type 2 star singularity, which has the form of an affine Dynkin diagram of E8 when we resolve the singularity. Beyond that, if we get 4, 6, this is bad, and it's looks at codimension 1, it's off at infinite distance in moduli space, and we don't get a decent Calabi-Yau. There's no Crepin good resolution of this whole thing. Okay, so this gives us a way of interpreting, on the geometry side, a whole class of interesting Calabi-Yau threefolds. Now, on the physics side, there's this beautiful idea called F-theory that was developed by Conrad Waffe and Dave Morrison, mathematician, in which, in this picture where we take some higher dimensional space, in this case we take what's called 2B string theory, we compactify it on, say, B2, and we get a 6D supergravity theory. We can also do it on elliptically fibered Calabi-Yau of higher dimensions. 2B, it turns out, has a thing called an axiodilaton, which encodes the complex structure of an elliptic curve. So I don't want to get too far into the physics, but the idea is there's a physical interpretation of any elliptic Calabi-Yau as a way of compactifying one of the string theories to a supergravity theory, which has gravity plus a set of things called tensor fields, B mu nu, plus gauge fields in some gauge group G, plus matter fields in some representation R of G. And F-theory is basically a dictionary which goes from geometry to physics. And let me just tell you a few pieces of this dictionary because it will be helpful in understanding what I say next. And really part of the theme of what I'm trying to say here is we're going to compare these toric hypersurface Calabi-Yaus to elliptic Calabi-Yaus. And we're going to find, first of all, that almost all of these things are, in some sense, elliptic or close to elliptic. And second of all, that this language of the elliptic fibration and in particular the geometric language of the geometrophysical language of F-theory gives us a great lens in which to sort of talk about which Calabi-Yau manifolds we have and think about their structure. I mean, normally if somebody gives you a Calabi-Yau in this way, you can compute what's called the wall data, you get all the triple intersection numbers, you get the second Chern class, you get the various other topological features of this. You might have a Mori cone, which tells you about the complex structure. But it's kind of obscure data, at least from my point of view. Whereas this geometric picture allows us to think about a Calabi-Yau as, okay, it's an elliptic fibration over this base with a certain gauge group associated with a certain divisor. It gives us a very visceral and geometric way of thinking about each of these Calabi-Yaus, which I think is going to be useful. So let me just say a little bit about this dictionary of geometry to physics. These codimension 1 singularities map to, in the physics language, the non-abelian gauge group. So for instance, if we have an E8 singularity, on the physics side, that corresponds to an actual E8 gauge group. We have SU2 and SU3. We get an SU2 cross SU3, which is the part of the standard model non-abelian gauge group. The Mordell-Weil group of the elliptic fibration, which is a pretty subtle mathematical object, is the rank of the set of sections, which is a little hard to compute, but we have a lot of constructions in physics. This corresponds to abelian U1 factors in the gauge group. Let me actually put this in a slightly different order, but let me just say a few more things. H11 of the base minus 1 becomes the number of tensor multiplets in the gravity theory. So we can read off a map between the physics and the geometry of the base. H21 of the total Calabi-Yau is the number of neutral hypermultiplets. There's the number of fields that are neutral, just neutral fields plus 1. There's a formula called the Chiyoda-Tate-Wazir formula for an elliptic fibration, which says that H11 of x is also equal to H11 of the base plus 1, which is the section. In other words, if we find, how do we find all the divisors in a Calabi-Yau? There's the divisors in the base, there's a section. If we have one of these non-abelian gauge groups, we get an extra divisor for every element of the Cartan element, every Cartan generator of that non-abelian group. And then we have the rank of the abelian group, which is the rank of the Mordell-Weil group in the geometry language. So Chiyoda-Tate-Wazir relates all these things. So the point is there's this rich interplay between the physics and the geometry. There is also a correspondence between the details of the matter, which can be understood both geometrically and in the physics side in terms of anomaly cancellation. I'm not going to dig deeply into that, but I will just mention that a given group, G, is associated with an anomaly coefficient, BI, and that BI corresponds to, let me call it CI on this side, or DI, which is the divisor supporting GI. In other words, these codimension 1 singularities live over divisors in the base. So there's a geometric correspondence between each of these gauge groups and something in the physics and the divisor that supports that. Okay, so there's this nice dictionary between elliptic fibrations and the geometry of Calabi-Yau threefolds. Okay, let me say a little bit more about elliptic Calabi-Yau threefolds. Okay, first off, while we don't know whether the number of Calabi-Yau threefolds is finite, there are a finite number of elliptic CY3s. Okay, and that was proven by Grossi and Gross. And it essentially comes from the minimal model program. If you take the base B, you can blow it down until the bases are just P2 Hirzebruch FM, where M is less than or equal to 12, and the Enriquez surface plus multiple blowups, one or more blowups of these. So we can get all the possible bases by just starting with these things and blowing up points repetitively. We can do this in the toric language. So with Dave Morrison, quite a while back, we carried out this program of starting with P2 and Hirzebruch. Enriquez is not so interesting because its anti-canonical class is just torsion. So we took these guys, blew them up as many times as possible. You can't get a curve of minus 13 or greater, C dot C bigger than or equal to less than or equal to minus 13, because if you have a curve of self-intersection less than or equal to minus 13, it gives you a codimension 1 singularity that's off the Kodaira chart and is bad and is at infinite distance. So there's an upper bound to how much you can blow things up. So we did this in the toric context, and we got 61,539 bases. We have a list you can download. Okay, so we have toric hypersurface Calabi-Yaus. We have elliptic Calabi-Yaus, which are finite, and a certain toric class of them that we've explicitly enumerated. Before I put them together, let me pause for a minute or two for questions and discussion, because the next thing I'm going to do is I'm going to take these two things and stir them together.
There were these recent papers by Birka and collaborators, how does this relate to this finiteness statement? So I thought this statement, which they proved some years ago, is weaker than what was in the recent papers.
So are these for higher dimensional Calabi-Yaus? There's some work by, I'm actually not, which papers are you talking about?
In 22, Birka and collaborators, I don't know if someone, maybe Richard knows the name that.
Richard, do you know what he's talking about?
Was this the talk at String Pheno where they bounded H11 from above by 6,000 and something as a theorem?
Yes, exactly.
Yeah. So,
Oh, okay.
yeah, so those are strong. So the results are weaker because they have less assumptions, but those are theorems. Here, this is, so the Grossi-Gross paper is a finite upper bound. Yeah, Wadi can take it from here, but it's the 6,000 upper bound.
Yeah, so there's a question which is for a non-toric elliptic vibration, how can you put a specific numerical bound on the structure of these things? And I think this is what this paper is addressing.
This is the more recent one.
And there's also some work by Heechul and others on the physics point of view where they put bounds, but those are based on a bunch of physics assumptions, which I wouldn't necessarily want to make in the physics context, in the math context.
Yeah.
So there are questions, but can we put concrete bounds on the size of these things? Torically, there's a strict bound that just comes from this. Non-torically, there's some other, yeah.
Let me just say, the way I thought about that paper by Birkar and them was they were basically morally trying to do the same thing as Heechul and Cumren did in their paper, just without all the physics.
I know which paper you're talking about. Yeah. They basically just tried to do the same thing without making physics assumptions, which is, I think, morally correct. Yeah, it's hard to put an upper bound on these things, and that's what they're working on.
I understand, but this is not. This is also what I mean. But there is also there is from 22. There's the original Birka et al. Paper where they give an actual finiteness proof of elliptic Calabi-Yau, which is stronger than the course.
So I think this is already a proof that there's a finite number of topological types. Yeah, I mean, we should talk. Let's talk offline. Yeah.
Sorry.
Yeah, please.
Is of Grassi and Gross where they prove finiteness of elliptic QHD?
What's that?
Which paper of Grassi?
So there's a paper of Grossi where she talks about the bases through using the minimal model, and then Gross. I don't have the exact.
So it's two different papers.
Two different papers. A paper by Grossi, which sets up some of the stuff, and then a paper by Gross, which proves the finiteness. And there's some more recent work by Dicerbo and Sfaldi on higher dimensional Calabi-Yaus, which also.
Yeah, this is the same group. Yeah.
Yeah, Dicerbo and Sfaldi they're also addressing the question of finiteness in higher dimensions. There are also some questions, especially in higher dimensions, about proving the finiteness of the number of flop equivalence classes, the number of chambers in the extended Kähler cone. I'm going to kind of elide those subtleties here because I want to get to the end of my talk.
Yeah.
Okay. Okay, so let me now mention a couple of punchlines, which we'll talk about in a bit more detail. So first of all, we have these two sets. We have these 474 million toric hypersurfaces. There's also a large set of what are called complete intersection Calabi-Yaus in products of projective spaces. And then we have these elliptic things. So the next thing I want to say is that most known CY3s are elliptic. And this was shown by Anderson, Gao, Gray, and Lee for the CCs, where they found something like more than 99.95% are elliptic. And for the toric hypersurfaces, both with toric hypersurfaces, sorry. For the toric hypersurfaces, both some earlier work with Yuchen Huang and this recent paper with Richard and Fatima shows that all but 29,223 of the 474 million are elliptic in some phase, meaning for any given polytope, there's a bunch of different triangulations. At least one of those one of the chambers of the extended Kähler cone has an elliptic structure. So they're all sort of morally speaking elliptic. The elliptic, so I'm addressing some of the questions that I asked at the beginning about the elliptic class. So I asked, is there a finite number of Calabi-Yaus? Are they all connected? Well, there's a finite number of elliptic ones, and most Calabi-Yaus seem to be elliptic, which sort of suggests that there should be a finite number of Calabi-Yaus. Furthermore, these are all connected. And it's pretty easy to see how they're all connected. They're all connected by transitions which could change H11 of the base, which are called tensor transitions, where basically we blow up a point in the base. All the Hirzebruchs in P2 are connected to each other by blowing up and down points. So we can move between the bases. Once we have a given base, we can move between different Weierstrass models just by tuning the Weierstrass coefficients, which physically has an interpretation as things like changing the rank of G, which are called Higgsing transitions on the physics side, and changing the representation of the matter, which are called matter transitions. So all the different elliptic fibrations we can describe in a common language using this F-theory picture. There's a finite number of them. And let me just mention that it's not only a finite number of elliptic, but there's also a finite number of genus 1 fibrations, which have a slightly more subtle interpretation in the F-theory language. The statement about connectivity is more transparent just for the elliptic Calabi-Yaus. Okay, all good? All right, let me talk briefly now about some of the results of this paper that just came out. So what we did in the paper with Richard and Fatima is to look explicitly at the elliptic fibration structure of all 474 million Calabi-Yaus. So 2 fibrations in Kreutzer-Skarka. So basically we find all 2D subpolytopes of a 4D subpolytope. So if we have a 4D subpolytope and it has a 2D subpolytope, then that implies that there's an elliptic fibration. You can explicitly construct from that a triangulation, which turns this into an explicit elliptic fibration. So we go through and just using computational methods, construct all of these things. As I said before, all but 29,000 of these 400 million have a fibration. We found 750,644,657 inequivalent fibrations. So you have to check whether they're equivalent by checking whether there's an automorphism of the ambient polytope. Modding all that, we get some 2.25 billion. For each one, the fiber is one of the 16 reflexive 2D subpolytopes that I mentioned. And the base, in other words, if we project out the fiber, we project onto some toric base, it's one of the 61,539 toric bases I mentioned that we enumerated with Dave, plus some singular bases, which we hadn't quite expected, but it turns out there's cases like, you can have a base which looks like this, where nothing projects to these guys. And this is actually a singular base, P2 mod Z3. And this is only with fiber F1, which has a 3-section and not a, so these three of the 16 fibers are not elliptic. They're just genus 1. They don't have a section. And for those cases, there's a multi-section. So there's a certain class of fibrations where the base is singular, has a Z2 or Z3 orbifold point, and those are always affiliated with a 2-section or a 3-section. Okay, so this is all great, and I would say this gives us a useful way to classify the elliptic CY3 intersect toric hypersurface landscape. We can use sort of the physics language to describe these things. Let me give you.
What can I ask something?
Yeah.
Just for understanding, so when you say each of them has one of these fibers,
Yes.
You still allow that there's kind of additional points in the fiber, which are the blow-ups of singularity.
Not in the fiber. Actually, the fiber will not have extra points.
So the fiber polytope is only the polytope.
The fiber polytope is the two-dimensional subplane, the intersection of the two-dimensional subspace with z to the 4, and that will only have the fiber in it. If it has anything more, it would not be a reflexive polytope.
Oh, but when you blow up if you
When we blow up the base, we get all kinds of extra points, but they don't hit the fiber.
so you have no gauge groups. That's what I'm.
No. Absolutely, we have gauge groups, but they don't live in this 2D subspace living with the fiber. For example, let me give you an example. We could take P231, right? And over this point, we could stack a complicated B2, which is huge in the extra dimensions. And there would be all kinds of points stacked up over these things here. But over this, we would just have the fiber. Sorry, if we took a 2D subspace, we have the fiber. We get extra points which live in the directions orthogonal to the fiber, but we don't get extra points in the fiber direction. The tops that you're talking about, those don't live in the fiber subplane.
I see.
They live over the divisors of the base, and the divisors of the base are by definition not in the fiber subplane.
I was thinking about the tops, and the tops, they will not only have these reflexive.
Absolutely, the top, but the top again is living, like if everything in pink here is out of the plane in the extra 2 dimensions, in the plane we'll only have P231. The tops all live out of the plane. They live over, even if it's say P2, the tops will live over this. It tells you what the gauge group on that is. There's all kinds of complicated stuff. We allow gauge group, all that stuff is there. It's just it doesn't affect this business here. Yeah. Okay, let me give you just one example just to give you a flavor of what this looks like. So I'm going to give you the example of what does a typical Calabi-Yau in the Kreutzer-Skarka database. So almost all of them have elliptic fibrations. So we have various statistics. You can look at the paper that came out last night. Different fibers, different bases have different statistics. What does a typical CY3 look like? And if I gave you this in terms of the Mori data, it would be some horrible thing. It would just be, hundreds of numbers, which would be hard to make sense of. But in physics, it makes a lot of sense. We have base 72, which is a generalized Del Pezzo. It looks like this. Drawing the toric divisors. We have a -2 curve here and a -2 curve here, and the rest are -1 curves here. So this is a toric generalized Del Pezzo. These are the self-intersections of the toric curves. This is our base, okay? And over that base, we have the gauge group SO7, SU2, G2, SO3. Sorry, there's something wrong with that. This is, sorry, SP3 and SO8. Okay, so with base 72 and fiber 6, there are 17 million 72.6 fibrations. So there are 17 million fibrations with fiber 6 and base 72. And a typical one looks like this. We've got a gauge group SO8, SP3G2, a gauge group SO7, SU2, a bunch of matter. This is the physics interpretation, but this is actually a nice, clean way to think about that Calabi-Yau. You can actually reconstruct all of the wall data from this picture. Okay, you can reconstruct all the triple intersection numbers. This is the base. You then have these gauge groups. You have Cartan divisors, the intersection numbers. Thomas has some beautiful papers where you compute many of the triple intersection numbers of a Calabi-Yau threefold based on the information about the gauge group. There's a little bit of intersection number missing, which has to do with the resolutions, and there's some options there. But up to those degrees of freedom, using Thomas's formulae, you can reconstruct the triple intersection numbers just from that picture. And again, this is just a typical Calabi-Yau. So the idea is all the Calabi-Yaus can be classified roughly in this way. Okay, questions? Lots more I could say. We have lots of nice, fun graphs and examples in the paper. Let me, what time did I start? Maybe 5 minutes past? Okay. Okay, then we're doing fine. Okay, so there's two more things I want to do. One is to talk about finiteness and connectivity in terms of this picture, and the other one is to talk about why we expect finiteness. So yeah, let me just pause it. Any questions about this? The basic idea is this gives us, I would say, a clear way of understanding the whole Kreutzer-Skarka database, essentially, except for a few examples, which we'll come to in a minute. We can look at any Calabi-Yau and say, oh, it has a geometry something like this. We have a base, we have a fiber type, we can think of the fiber and the Weierstrass model as encoding certain gauge groups, and that gives us kind of a real handle on what kind of an object we have. And among other things, that will help us understand transitions. Like if we go from one Calabi-Yau to a related Calabi-Yau, that will involve a slight change of the gauge group or the matter content. So it's a physics language for describing this entire database of 470 million known Calabi-Yaus. Yeah.
When you give this very precise number and you say inequivalent for it, so you have checked that they are all inequivalent, and it's
Yeah, Richard did that.
What kind of equivalent? I mean,
Okay, so the idea is you could have the same polytope. Like, let me give you a very simple example. Let's take a polytope with vertices 1, 0, 0, 0, 0, 1, 0, 0, minus 1, minus 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, 0, minus 1, minus 1. That's, in some sense, P2 plus P2, right? It's a copy of P2 in one pair of dimensions, a copy of P2 in another pair of dimensions. That is this is fiber 1 over base 1. Like, it turns out P2 is both fiber 1 and base 1, but it's also fiber 1 over base 1. There's an automorphism of the polytope, which maps, this into this, and this into this, and this into this, and there's other automorphisms which like exchange these two. So there's like some kind of, I don't know, Z2 cubed or bigger automorphism group of this polytope under which the fibration structure remains invariant. So we treat those as one inequivalent fibration structure.
that's what I'm asking is, are you saying that for any two of them, there's no fibered biholomorphism between them, or are you saying just a combinatorial data? I mean, did you prove that they actually?
Good. We have not shown that this is just the equivalent at the level of automorphisms of the ambient space. It is possible that there are equivalents that are more subtle. I think Richard and the Cornell group have identified a few cases where you can get the same Calabi-Yau through what look like rather different, even through different polytopes. And we're not considering that kind of equivalence. Surprisingly, that kind of equivalence is very rare. I mean, I'll just tell you one more example since I'm going to have 10 more minutes. One nice example that we have is if you take the base P2, in the physics language, so the generic elliptic fibration here is the one which has Hodge numbers 2, 272, right? This is the number of basically complex structure moduli. H11 of the X is H11 of the base, which is 1 plus 1, which is the fiber. In the physics language, we could tune an SU2 on n times the plane, okay? So you could tune an SU2 on a line, or you could tune it on a quadratic or on a cubic, and there's a whole story about what the matter content looks like. And you can do this for n up to 12, and something interesting happens for 9 to 12. There's some extra structure which is forced on you called automatic enhancement. I won't go into that. But for each of these 12 possibilities, you can imagine a Calabi-Yau just by constructing elliptic fibrations. Don't worry about toric hypersurfaces. So we checked, and in fact, all 12 of these, including the business about automatic enhancement, are included in the KS database, which is kind of surprising because there's a gauge group tuned over a non-toric divisor, right? I mean, Thomas mentioned TOPS, which are a way of tuning gauge groups over toric divisors. So it's pretty well understood in the literature, how do you get a gauge group of SU2 on H? But it's not as clear how you get a gauge group of SU2 on 5 times H. And it turns out they're all there, and they're all there exactly once. So many things that we look for are there exactly once in the database. So for n1 less than or equal to n less than or equal to 12, there's a unique example in the Kreutzer-Skarka database. So that's a case where there are not equivalences beyond the ones that we're modding out by. Your question is great. In fact, we're looking for other cases of that, but it's actually surprisingly hard to find equivalences. Somehow the fibers give us different enough structure that it's relatively rare. I don't know, Richard, if you want to add anything to that.
I sort of feel combinatorially like it has to happen somewhere in the database that there's two triangulations that are isomorphic even though they live in different polytopes. I tried, I couldn't find any. Now I think there's a reason why I can't find any, but yeah, I think that to find them you have to look at big H11, and a big H11 the computation is just too hard to do. But yeah, I don't know of any cases where it happens.
Yeah, and just to emphasize, so this gives us information about gauge groups on non-toric divisors. I will just mention one other interesting thing, which is we've been looking at toric bases, but in many cases, there are singularities of codimension 2, which are this 4-6 type in the Kodaira class, which in the physics language give us something called an SCFT, which are associated with non-flat fibrations. And those actually implicitly involve blowing up the base. So for instance, Volker Brown years ago did a similar class, basically the same classification just for the base P2. And he found, I don't know, what is it, 273,000, I don't remember what the number is. 200 and something thousand different fibrations over P2. And one of them is an SU27 over H on P2. And that violates anomaly cancellation. So in this paper, we've understood that in more detail by noting that there's 3, 4, 6 points. And actually, you have to blow those up. So instead of having the base P2, which naively would look like this, we actually get a base that looks like this. Where we get an extra -2, -2, -1 curve where we have SU27, and these are all SU18, and these are all SU9. So we get a much bigger gauge group on a non-toric base. So the point is that this database, while ostensibly just toric stuff, encodes all kinds of divisors on non-toric, gauge groups on non-toric divisors and non-toric bases through resolution of SCFTs. So it's actually much more comprehensive than you might have guessed. All right, I'm getting into my last 5 or 6 minutes, so let me tell you 2 more things. Finiteness and connectivity. Okay, so let's talk about connectivity. So first of all, we have only been considering reflexive polytopes. We can consider a bigger set of polytopes, which includes the condition that the dual polytope have the origin as an interior point, but drops the condition that it has to be a lattice polytope. So let's just say Nablus star contains the origin as an interior point. This is a much bigger set. There are on the order of 10 to, well, let me write it as, there's 10 to the order of 25. We can calculate this fairly accurately using some statistical methods we developed in a recent paper with Yinan Wang and his student Yihang, but we're still in the process of that. But it's on the order of 10 to the order of 25 polytopes, far more than 400 million. You will still have a Calabi-Yau for an anticanonical hypersurface, but it will include some singularities. So that's one step is let's go to a broader class of polytopes. These are actually all interesting to physicists. As I mentioned, these superconformal field theories that come with these 4-6 points, those are not points we want to ignore, even though they're singular Calabi-Yaus. Those are points with interesting physics that's different. There's been a rich study in recent years of 6D SCFTs. So all these Calabi-Yaus will include all kinds of interesting singularities. Okay. Once we go to this set, they're all connected by a single move, which is plus or minus array. That is, if we start with, these things live in some big sets, some big boxes, and everything inside that box is going to be a good polytope from that point of view, and we can get a smaller box by removing a single ray one at a time. So they're all connected, and these involve various extremal transitions. The simplest one is like a type 2 transition. There's also type 3 transition. Type 2 is where you take a divisor in the Calabi-Yau and shrink it to a point. But again, this will now involve some singular intermediates. I should add that there was some related work to this done years ago by Kreutzer-Skarka and by Avram et al. But this idea of going to all these polytopes, I think, which is what we're doing with Laura Anderson and James Gray and with Richard, gives a much clearer picture. So this connectivity, we can connect to the connectivity we know of for elliptic ones through the Weierstrass model. So this is basically extending the connectivity of the elliptic fibrations through the Weierstrass models to a connectivity of all the Kreutzer-Skarka polytopes. Okay, let's look at the 29,000 non-fibered polytopes. How do they fit into the web of Calabi-Yaus? So we did a nice little calculation. And we found that they can all, every single one of them, can be put in a fibered form with one move. That is to say, if we take a polytope that is non-fibered, we can add a single ray to the ambient polytope, and that then gives us a fibered, an elliptic or elliptical genus 1 Calabi-Yau as a hypersurface, as an anticanonical hypersurface, by just making one move. It might be singular and it might not. Looking at this a little more in detail, of those 28,100, I told you I was going to give you data, 28,106 with one move, you can go to another reflexive polytope. So in all but 3% of the cases, you can go from a non-elliptic, non-fibered Calabi-Yau to a fibered Calabi-Yau by blowing up a single thing into a new divisor and get a good Calabi-Yau that's smooth with no issues. So that's nice. And then there's like 1,000 other cases. 966 of them need one extra ray. That is, you blow it up and you get something which is elliptic but singular, so you need to resolve one more divisor to make it a nice smooth Calabi-Yau. So now all of them except 151 require more than one extra ray, and most of them just require 2 or 3. There's one anomalous case that requires 14 extra, but every other one requires only 6, up to 6 extra. Just as an example, if we take the quintic, so the famous, quintic hypersurface in CP4, this is everybody's favorite simple model of a Calabi-Yau, which is, among other things, not elliptic. This does not have a fiber. But if we add a single ray, if we add that ray, 0, 0, 0, actually, sorry, let's add 0, 0, 0, minus 1, minus 1. That thing is elliptic. So that's one transition that gives us something which is elliptic. It's a little complicated, that transition. Okay, I'm just about out of time. I just want to say one more thing. Can I have 2 more minutes?
Yeah, you're fine.
Okay, great. Okay, we're finding that there's a huge set of Calabi-Yaus. Most of them seem to be elliptic in some moral sense. There's a finite number of elliptic ones. All the elliptic ones are connected, and furthermore, the other ones we know of are connected. And there's some similar results to this, which we'll have in the paper with Laura and James about CC, is that they're all also connected. So let me ask this: why should most CY3s be elliptic? And there are some results. I think Wilson and others have made arguments in this direction in the math literature. Let me just say a few things about that. There's a theorem by Oguiso. I'm going to quote other people's theorems, as I said, but no theorems from us. Theorem by Oguiso and Wilson, which says that a Calabi-Yau threefold is elliptic if and only if there's a divisor D so that D cubed vanishes. This is called a Kolar divisor. Basically, it helps us pick out where the section and the base are. So that D cubed is vanishing, D squared is not equal to 0. That avoids it being a K3 fibration. And D dot C is greater than or equal to 0 for all algebraic C in the Calabi-Yau. So all we need to do to show that something's elliptic is to show that D cubed equals 0. If we have a large H11, this is basically solving a cubic equation over the rationals, right? So what are the possible obstructions? The first possible obstruction is number theoretic. We have some random cubic. Can we solve that over Z or Q? A number theoretic obstruction would say that there's no solution of that over Z or Q. So Mordell, I think back in 1929 or something, came up with degree D polynomials in D squared variables with such an obstruction. And then there was a conjecture that Mordell's result was as bad as it could be. That is, that if you had more than D squared variables, that you would not have an obstruction. And in dimension 1, that was proven. In dimension 2, that was proven. In dimension 4, there's a counterexample with an obstruction and 17 variables. There's a result of Heath-Brown for 3. 3 is the case of interest to us. It says that any non-singular cubic in greater than or equal to 10 variables has no obstruction. And that's been generalized to say that any general cubic in greater than or equal to 16 variables has no obstruction. And what that means is there's no number theory obstruction at H11 is bigger than or equal to 15. Let me just, I didn't do this before, but the set of polytopes in the Kreutzer-Skarka database gives us a distribution of Hodge numbers, H11, which goes out to 491, 11, and 11, 491. So 15 is pretty darn small compared to that. It's like dividing line here. So basically, there can't be a number theoretic obstruction anywhere out here. Okay. If we take kind of a statistical point of view, the only other obstruction there could be is a cone obstruction. And if you just, I'm short of time, so I won't go through the argument. It's pretty simple. In a paper with Yuchen Huang, we argued that if you assume that the Kähler cone is a positive orthant, then basically just by writing down cubic equations in an increasing number of variables and assuming that everything is independent, all the triple intersection numbers are independent with no conspiracies, you find that the probability that something is not elliptically fibered, that is, that it does not admit a Kolar divisor, goes something like 2 to the minus H11 of x. And that exactly matches the data. So I told you about these 29,000 that aren't elliptically fibered. They decrease almost exactly according to that 2 to the minus H11. So there's kind of a general argument, which is not a math proof, but it's just an argument based on some statistical assumptions that if the triple intersection numbers are independent, this should be the rate at which the probability that you're not elliptically fibered goes down. And it exactly matches what we see in the data. So it seems pretty plausible. Okay, let me just conclude. Summary, most known CY3s are elliptic, 99.99% of the toric hypersurfaces. F theory, this language of F theory and elliptic fibration is a great organizational tool and lens to understand the structure of all these Calabi-Yaus. The elliptic Calabi-Yaus are finite and connected. The non-elliptic, both for the toric hypersurfaces, and I didn't get into, but also the CCs, are connected to elliptics with one move each for the known ones in those big classes. The probability that you're not elliptic goes down as 2 to the minus H11. So this is not by any means a proof. And maybe there's some kind of lamppost effect. Maybe there's some crazy set of non-algebraic Calabi-Yau threefolds that nobody's written down that's totally outside this framework and totally violates everything I've just said. But all this data suggests that probably, from a simple physicist point of view, the number of Calabi-Yau threefolds is finite, the number of topological types is finite, and they are connected. And so I guess the question to all of you is, can you find a way of making this all tame? That's my story.